transformation. F1 and F2. Let's say 2x squared and 1/2 x squared. I'm asking, of course, the same questions always. Which base function was used to create F1 and F2? Perfect. Let's graph it. Here's x squared. We know the graph. Can you give me a couple of points on this graph? Let's say when x is 1, not on these, just on the base function. When x is 1, I would like to graph it larger, bigger.
1, y is 1.
Good. So 1, 1.
2, 4.
2, 4. That's all I need. That's good enough. So here's the graph of x squared. Good. So now we analyze in the same way. I have x squared, and here's 2x squared. I can only change x or y. So am I changing x or am I changing y?
X.
But I have x squared, and I have x squared. So this is outside. It's not inside. Remember when we changed x on this graph, right? When we changed x, we changed it to x plus 1. When we changed x, we changed it to x minus 4. So I'm changing y. I'm changing y. So can anyone give us the y value when x is 1? Because I want to know where it's going. So for this function, when x is 1, y is 1. Clear. Now for this function, when x is 1, y is 2. Also, for the same function, when x is 2, y is how much?
8.
Yes. 2 squared is 4. 4 times 2 is 8. So bear with me. I'm going to say this is 8. So here's what happens. This is twice x squared. So here's x squared. When I multiply it by a number greater than 1, which means I change the y values corresponding to each and every x value, here's what happens. So from x squared, twice x squared is this. We call that a vertical stretching.
Right.
Yes, this is a vertical stretching. So when the number in front is greater than 1. So 2x squared vertical stretching by a factor of, that's true too. I'm going to get to that in a minute. Very good. Okay, so let's look at 1/2 x squared. Give me a couple of points. So let's say when x is 1 for 1/2 x squared. When x is 1, how much is y? Right here. When x is 2, 4 divided by 2, which is 2. So exaggerated on the left-hand side. Sorry about that. It's a little bit less. Okay, so this is 1/2 x squared. So when we multiply x squared, outside of course, by a number less than 1, what happens? When I multiply by a number greater than 1, this happens. When I multiply by a number less than 1, this happens. So what do we call that? A vertical shrinking of the graph. shrinking by a factor of 1/2.
It's also horizontal stretching.
True. So 1/2 x squared is vertical shrinking. Vertical shrinking of the graph. So coming back for a second to our list of transformations. We talked about this, and the vertical stretching and shrinking. We're down to the last one. Any questions so far? Okay. Last one, and then we'll look at either a word problem or an application of this. Okay. F1 of twice x and F2 of 1/2 x. I did not give you the function, but we're going to look at the function in a minute. What am I changing? It's obvious what I'm changing now.
X itself.
X from plain x to 2x or 1/2 x. That's clear, right? Okay, so let's use, I'm giving the function f of x, x cubed. So bear with me. And if I use f of x equals x cubed, I'm asking you to find f of twice x. Maybe I shouldn't even name them differently because they are all referring to this function. So anyway, so f1 is this function of twice x. So how do I determine f of twice x for this?
Simply plug it into x for x.
Very good. Awesome. So what do I get?
2x cubed.
Which is?
Cubic?
2 to the third power is?
Oh, 2 to the third.
8x cubed. What about the other one? In the same way, 1/2 x to the third power, I get 1 over 8x cubed. True?
Yep.
Well, there is no surprise there. Tom was already 5 minutes ahead of me. So if I graph this function, we graphed it today, I get this graph, right? So don't look at this and tell me how will I graph 8x cubed based on what we just discussed 3 minutes ago.
It's gonna be stretched a whole lot.
Do you agree? So this is x cubed. 8x cubed will be this. I'm exaggerating. But he already said it. What happens horizontally? One more time. This is x cubed. When I multiply x by 2, what will happen here? So what type of transformation is this on the horizontal? Horizontal?
Shrinking.
Shrinking. This is the one that maybe is not obvious like the other ones. So this, you would have expected that x is multiplied by 2, right? So that the graph becomes much wider. No, it's the opposite. So when we change x into twice x, this is a horizontal shrinking of the graph. Horizontal shrinking of the graph. What happens here? Let's do this together again. So this is x cubed. When I change x into 1/2 x, what happens now? Right. At the same time, horizontally, it's a horizontal stretching. So this is a horizontal stretching. I have to be honest, this is a little bit less used in your course. It's very important for trigonometry. But since this course does not look at trigonometry at all, this is very important, more for trigonometry than for anything else. Okay, so let's take a look at, I'd like to look at a problem here. We are on page, don't forget to review these problems, please. Okay, page, and here's the reason why we study this. Not the only reason, but here's an idea. I'm sure you're thinking, okay, so how will I apply this in real life situations? Well, there are many people who all they do is they try to find models that reflect situations in real life. So for example, if let's say they measure 1,000 people's blood pressure after they take a medication, and let's say they plot those points that they get like this. Or maybe they check tires for braking distance on wet pavement or dry pavement, whatever. And let's say they graph something like this after they test them. And I can go on forever. What will you suggest the factory or the researcher or the medical personnel? What kind of function will you think of this? What will you say? Hey, I think that a function like this will fit your model.
Square root of x.
Exactly. Shifted to the left and then up.
Mm-hmm.
What would you say to the other group of people when they plot something like this or similar? What will you say? Hey, I think I have a function for you, which is right. Shifted to the left and then down. Because now we have the knowledge of how to create new functions using transformations on base functions. Okay, so let me look at a problem like 128 on page 296. And then I don't want to forget, I want to go back now to the piecewise-defined function. Okay, we are given a function f of x, 3.1 times the square root of x and plus 19. Here's what they say. They say that it models the median height. I'm taking notes when I read. This is the median height of girls who are X month of age, X months, or age in months. The graph of F is shown. Here's the graph. It's very clear. It's a vertical stretching by a factor of 3.1 and up 19, which we know now. Here's the first question. That was a question, the first question. Describe how the graph can be obtained using transformations of the square root function. So what will I say? Number one, vertical stretching, 3.1, and then up or shifted up, 19 units. Very good. Number two, question number two. According to the model, what is the median height of girls who are 48 months or 4 years old? So when X equals 48 months. How do I determine the median height?
Simply solve, but we'll plug in 48 for x. Right?
So in y equals, let's do that, 3.1 times the square root of x, and outside plus 19. Do we have the function in?
Yeah.
I think nobody's working with me on this. Okay. So then I go to second end table. And I will plug in what I want. And I want 48. And I get 40.477. So f of 48 equals 40.477. What does that mean? Use a calculator and round to the nearest tenth. So I'm going to round it to 40.4. And what is the measurement unit? Without measurement unit, it means nothing. Inches. Inches. So girls at 48 months old, according to the model, they should have a height of?
Average out at 40.5 inches.
Yes, a median height of 44. Yeah. The actual median height for girls at 48 months is 40.2 inches. So actual is 40.2 inches.
Close.
How well does the model describe the actual height?
Close.
Very close. Very close. I will say this. At the age of 48 months, the model appears to be very accurate. I don't know outside of that. I don't know if it's at 60 months will be the same. I don't know if at 12 months is a good approximation. That part I don't know. So I will say at 48 months, the model appears to be pretty accurate. So at 48 months old, model, pretty good. If I deviate from 48, I don't know. I have to check. Model, pretty good, pretty accurate. Next question. Use the model to find the average rate of change in inches per month between birth and 10 months. The average rate between birth and 10 months. How do I determine that? What was the formula for the average rate of change of a function between 2 points?
Y2 minus Y1.
Very good. F of x2 minus f of x1 over x2 minus x1. Perfect.
For a second, I thought we were going into intervals or always at limits.
Limits, the average rate. Yes.
I don't know why I thought they were intervals. But
so that means f of 10 minus f of 0. I'm going to erase this second parenthesis. I'm sorry. 10 minus 0. I don't know why I put it there. No excuse. I go back to my chart, and what do I plug in now? Of course, I will plug in 10 and 0. So back to my chart. Here's 0, and here's 10. So 28.8
plus 19 divided
minus 28.803 minus 19 divided by 10. F of 10 minus f of 0 divided by 10. What do I get? So 28 minus 19 is 9. So 9.8 divided by 10, which is 0.98. Measurement unit. If you remember, I mentioned last time when we looked at the average rate of change, the average rate of change has a measurement unit that is a ratio of 2 measurement units. The measurement unit for the top, from the top over the measurement unit for the bottom. So what is the top measured in? Inches. What is the bottom measured in? Exactly. So this is 0.98 inches per month. Per month. So between 0 months and 10 months, these girls increase their height or grow at the rate of awesome, at about an inch per month, between 0 months and 10 months. Okay. Last question here. Find the use the model to find the average rate of change in inches per month between 50 and 60. So final question, the average rate between 50 and 60 months. Of course, it's the same thing. F of 60 minus f of 50 over 60 minus 50. But my question to you is this. We haven't calculated it yet. Do you think that this will be bigger than that, or that is bigger than this? Other than Tom.
Actually, I don't know. How would I know?
Okay, so here's the question. Do we grow faster between 0 months and 10 months, or we grow faster between the age of 10 and 11?
Definitely between birth and 10 months.
Right. So I expect that this is smaller than that, roughly.
I was just speaking mathematically.
Mathematically, okay. Good. So I go back to my chart. I plug in 50 and 60. 50 and 60. So I get 43.012 minus 40.92 divided by 10. So how much is that? So 43 minus 40 is 3, but it's 2, right? So it's 2.1. So 0.21. I'm sorry, 1. 2.1 divided by 10. So it's just 0.21. Measurement unit, please.
Inches. Right?
It's a ratio. It has to have a measurement unit that is a ratio.
Inches in months.
Inches per month. So between the age of 50 months and 60 months, the girls grow at a rate of, at a
1/5 the rate
of between 0 and 10. Awesome. Very good. Okay, let's look at the piecewise defined function that we picked. This is the end of new material for the test. This is it. Yes, we have to practice a little bit more with transformations. So here is the function that we picked. It was x plus 1 for x less than -2, and it was x squared plus 2 for x greater or equal to -2. Now you understand why I wanted to wait for this, so you can tell me what it is. What is this? What transformation is on x squared? Is it a horizontal shift or is it a vertical shift? Going
up to.
That's it. That's why I needed this, so we don't have to worry about it. Good, very good. So then, first thing that I have to find is the domain of this function. If I'm asked to graph it, I have to find the domain. Very good. So I need this to be changed into interval notation. And then we'll fill out the chart.
Just write an R with a line through it. R represents all.
That's true. That's true. We don't use it, but we normally write x in like this. But we don't use this in this class. You don't have to worry about it. Tom is right. So x less than -2. So what is the interval notation for this?
I'll let you guys have a chance.
Finally, you're on my side.
On your side since about last class.
Good.
Negative infinity to.
Thank you, Eddie.
-2.
With a parenthesis.
Okay,
Yes,
yeah.
you're right. Perfect. What about this one?
I'll give you guys another go. Did a good one last time.
He's so generous today. Because there is
Because
no
it
equal
doesn't teach
symbol.
you
There is no equal symbol.
Every number up to, but not including it.
So this one will be -2 to infinity. Now from here, it's even easier to identify the domain. Can anyone give us a domain other than Tom? Because he already said it. All your numbers. You see that? From -infinity to -2, -2, and from -2 to infinity. It is all your numbers. The next step. Which x value must be in the chart?
-2.
Yes. Can anyone explain, other than Tom, why? Why I need -2 in the chart? That's exactly it. Good. So now, please pay attention if you are using my method. Let me explain what happens. Under -2, I will write a parenthesis facing left. Also under -2, I will draw a bracket facing right, and they will be touching each other. Why touching? It's because the function is defined at -2.
In open point, that's plugged in at -2 with the
Very good.
function that.
Which function do I use for x between -infinity and -2?
X plus 1.
Will you all see that? Do we all see that? Yes? Which function I use between -2 and infinity?
X squared plus 2.
X squared plus 2. Which type of function is x plus 1?
Linear.
Awesome. Which type of function is x squared plus 2?
So you got it much right.
Awesome. Good. So let's see what we have on this side. I only need 2 points on this side. Let's look at -3. Please plug it in and give me the answer for y.
-2.
Very good. Please plug in -2 and you should say no. I'm not allowed to plug in -2 because it's a parenthesis. True, but we will leave it open.
-1.
-1. Right here inside the parenthesis, I put -1. Now with -2, I plug it in the second function.
-2 squared, that's 4 plus 2, 6.
So it's 4 plus 2 is 6. Now please plug in 0.
2.
We can plug in another point if you want. Let's plug in another x value. Let's plug in also 1. What do we get? Very good. Is this clear? Notice one more time. -1 is inside the parentheses. 6 is inside the bracket. And now please give me the first ordered pair from left to right that you want me to plot so we can graph this function. And of course, yes, we established the domain is all real numbers. And then I will ask you about the range in a second after we graph it. So first ordered pair from left to right, what will you ask me to plot? Perfect. -3, -2. Perfect. Next ordered pair.
-2, -1.
Question now. Is this a full point or an open point?
Open.
Yes, indeed, because I was not really allowed to plug in -2. And you cannot stop at -2.5 or -2.1. You can't. You have to go to the closest possible point to x equals -2, and we don't know what it is. That's why I have to plug in -2 and leave it open.
Well, we do, we just couldn't plug it in and take an infinite amount of time because, infinite nines.
I agree.
After
Yep. Next ordered pair, please.
-2, 6.
So it's -2, 6. Full point or empty point? 0, 2 is the next one. And 1, 3 is the next one. I already know how to graph. I just graphed x squared and then x squared plus 2. But you cannot extend it to the left. You can extend it to the right, but not to the left. Please always remember the piecewise defined functions cannot overlap like this. That's not a function even. So each function is defined or graphed on its little piece or big piece. It doesn't matter. They are both big pieces. So the purple function is only graphed between these two. The blue function is only graphed between these two. You cannot extend the blue graph to the left or the pink one or whatever this color is to the right. Is that clear?